still correct. But does not tell the story. We will have a closed loop transfer function for all of the inputs to the closed loop system.
Oh.
So what are the inputs to the closed loop system? Which one? Huh? What are the inputs? I have no idea what that's going to be. Huh?
My sneeze scared him away.
Oh, you sneezed?
Yeah, I felt that you sneezed on him, and he was like, oh.
Whatever. Keep it. Okay.
Yeah, that's true. That's true.
All right, let's continue. So, now the inputs to the closed loop system, instead of u prime bar, I have the set point. There will be a transfer function for each of the closed loop system inputs. Normally, this is often called the closed loop transfer function. That is between the set point and the measured output. And I'll have a transfer function for each disturbance, but they're not going to be the same as the open loop transfer function. So I'll put that super CL to differentiate between them. So even though for the closed loop system equation 1 is still correct, the equation that will tell me what happens to the system, for example, am I stable or not? Now that will depend on the poles of the closed loop transfer function. Will I have oscillations or not? That depends on the poles of the closed loop transfer functions. Andrea?
What is the small circle? You have a purple one and a white one.
Okay. This shows the boundaries of the system if it's open loop. The white one, so what comes from the outside, if it's open loop, U prime comes from outside, and the disturbances come from outside. If it's closed loop, it's the purple boundary. U prime doesn't come from outside. The set point comes from outside. So that's what I was trying to say. Closed loop boundaries, and the white circle is open loop boundaries. Okay. Hunter? Claudia? Doing okay? Okay.
Dr. Svaranos.
Yes.
What do you mean by still correct?
It's still correct. This is still correct, but it doesn't tell the story.
What story?
For example, I'm going to have oscillations or not.
Okay.
That will depend now on the poles of the closed loop transfer functions. Okay? So everything that we talked about, different transfer functions, etc., for the closed loop system depends on closed loop transfer functions. What are those closed loop transfer functions? We can get them through some simple algebra. Let's get them. So let's find what these guys are. Okay?
Quick question, is GCL a function of S as well?
Yes. Did I put a verse? Oh, let me put a verse. Yeah. All transfer functions are in general functions. So let's get the closed loop transfer functions. I will start with equation 1, and from equation 1, we'll end up at equation 2. Using the control law, what do we have? We have equation 1 is still true, but in addition, I have that u prime bar is so. y prime bar equals GU of S, U prime bar, and you'll allow me to use the sum induction over I, GDI, DI prime. But that doesn't tell the entire story. What I need to tell the entire story. I also have that U prime bar is GC of S, E bar. And I also have that E bar is set point minus measure. All three equations that we tested. Okay? Now, let's call, I use the equation 2 there, so let's use that 1b in this equation. Here, okay, that. Use 1b to replace U prime bar in 1. So using 1b, we get y prime bar equals GU times GC of x, E bar, plus the sum of all disturbances of the I. And now let's use 1c to replace E bar. Now I have a relationship that has eliminated U prime bar, and what does it have? It has in it y prime bar, and all the inputs to the closed loop system, the disturbances, and the set point. To find the closed loop transfer functions, I need to bring it in that form, where I would have to have y prime bar equals something. So it should be obvious what I'm going to do. I'm going to move the y prime bar that you have here to the left-hand side, factor y prime bar, and divide by what you want. So let's do it. So moving to the other side, what do I have? I have GC of S, GU of, oops, what did I do here? GU of S. This is supposed to be GU. GU of S, GC of S. Please make a correction here. I miswrote. It's supposed to be GU. Okay, that's this GU. Equals, times y prime bar, this is the other side, equals GU of S, GC of S, set point plus sum of GDI of S, DI prime. I can factor y prime bar. This here can be rewritten as 1 plus GU of S, GC of S, times y prime bar. And then divide by the bracket. And I'm getting that y prime bar equals GU of S, GC of S, over 1 plus GU of S, GC of S, times y prime bar set point, plus the sum over all disturbances. I have GDI, and I'm dividing by the bracket. So GDI of S over 1 plus GU GU of S, GC of S, the I point. You should have. Everybody see that? What is this ratio? Just numbers and S. It's a transfer function. This is my GCL of S. I lost my order. I know you don't see the purple very distinctly, but you can still read the purple, right? If you have a good light, right? You can still see that, right? Anybody cannot see the purple? Maybe you can see the purple, okay. So this is GCL, okay. And this here, is our GDI of this. GDICL of this. So you can say that when you have automatic, equation 1 is still true. We use that to obtain that equation. But whereas on manual, we didn't have this relationship, that was the input. Now we have these two relationships, and the input is the set point, and now the equation changes to that. So I can write down here that GCL of S is GU of S, GC of S, over 1 plus GU of S, GC of S, and GDI, closed loop of S, is the open loop disturbance transfer function divided 1 plus GU of S, GC.
Can we work this out with an example, by any chance?
This is general theory. I mean,
I know, but how it applies to a situation?
that applies to what?
To a situation?
Well, you're doing control, it's what we get out of it. Now, what do we know from a transfer function? For example, stability.
You're just
What is required for stability? That all poles have negative real part. What required for stability now of the closed loop system? That all poles of the closed loop transfer functions have negative real part. Everything that we learned about system behavior from transfer functions applies now to the closed loop system with a closed loop transfer function.
You're just deriving those equations right now, right? The ones
Yes.
that we- Yeah. So it's the same thing, just different equations.
I know this is a conceptual class, guys. I'm trying to do my best to transfer the concept, but I can't give you an example of this because that's it. It's a concept. Give me an example of the law of gravity, okay? I can't. That's the law of stability. One important thing to notice. What are the poles of a transfer function?
Bottom numbers.
The roots, which roots?
The number.
Of the denominator.
I said
What are the poles of the closed loop transfer functions? The roots of the denominators of the closed loop transfer functions. Here is the closed loop transfer function with the set point. Here are the closed loop transfer function with disturbances. What do you notice about the denominators? They are the same. All closed loop transfer functions are the same denominator. Stability of a closed loop system requires that all the roots of 1 plus GUGC have negative real part. Absence of oscillations, that all roots of 1 plus GUGC are real. Okay? So that's the condition for stability of a closed loop system. So you can have GU and GDI, in particular GU, unstable, but 1 plus G, the roots of 1 plus GUGC, all negative. So you can have open loop unstable, closed loop stable. But you can also have the reverse. Open loop stable, closed loop unstable. So that's what's going on with closed loop systems. Now, remember what is another very favorite of mine equation that we get from equation 1 that I have used a lot in exams, all the exams, homework. Do you remember a consequence of equation 1 that we used quite a bit?
Steady state?
Yes, thank you. The steady state offset.
You stole it.
And the steady state value, right?
Yeah.
Final value theorem. Remember from 1, I just erased it together.
Did you give her this?
So from 1, we have
Oh,
if
that's or no? No.
limit
She didn't ask me.
s equals to infinity
Just throw it
of
You took
y
it.
prime of t exists,
Because I have too much paper now.
we'll have that y prime infinity
Like I
is
have no more
g2
space.
of 0, y prime, u prime infinity plus sum of gdi of 0, di prime infinity. Okay? We can do exactly the same thing with equation 2 for the closed loop system. You have this picture in your note, right? I don't think I'll use it again, of course. 5 minutes after I erase it, probably I will need it, but then. From 2, we have that if limit still goes to infinity, and the tip for closed loop system, two follows that y prime infinity is now, instead of g to 0 y prime infinity, will be GCL of 0 y prime set point infinity, a new set point deviation, plus sum of GDI CL of 0 di prime infinity. What is the error I'll have at the steady state? Well, it's the difference set point and measurement, right? E infinity is set point infinity minus, right? Error is set point minus measurement, or set point deviation minus measurement deviation, they have the same nominal value. So the error at infinity, the steady state error, is the difference between y set point minus y. So, if we plug from the above equation, that is equal to GCL y prime set point infinity minus GCL of 0 y prime set point infinity minus sum of GDI CL of 0 di prime infinity. Or 1 minus GCL of 0 times the set point new steady state value minus sum of GDI CL of 0